Welcome to All Distributions 2. So this is a class in which we're going to continue talking about the thing we started in our first All Distributions class, which was amazing. This time things are going to make more sense. First disclaimer, this is not a replacement for the book. So now we're talking about, you're getting started with your Pro module, so you know that you're going to have to read, okay? The book is there. It's a great book. I recommend that you read it. It's open source. Just go and read it. And it's important that you learn and you come to class, but after you go and you read the book, right? Just to put things to practice. It's because, again, we keep talking about this, right? Stats is a language, and we're trying to learn this language. And you can only learn a language if you practice. So the things that I call main number, for example, the book calls sample statistics. So you have to learn how to draw these parallels, okay? And learn how to read the book through the lens of what we go through in class. Cool. So let's start talking about sampling distributions. So there's two kinds of sampling distributions, okay? We have a discrete and we have a continuous distribution. So a discrete sampling distribution, and discrete numbers for that matter too, they are these numbers that are integers, right? So it's 1, 2, 3, 4, 5, like they're like a full number, right? And they're usually represented, these distributions are usually represented in histograms because you have a certain value that, you can find. Continuous is what you usually use in daily life, especially if you're working with Likert scales and stuff like that. These are all the possible numbers, right? All the decimals in between 1 and 2, 3 and 4. So there's infinite possibilities, and that's why we use this probability density curve as a visual representation of our sampling distribution, because it's continuous, and we're trying to estimate the probability of each particular value, okay? It's beautiful. Mathematics is amazing. But here's both of them for comparison. Okay, now we're going to talk a little bit about the discrete, though. So let's focus on the discrete sampling distribution. So let's talk about this candy example, okay? So let's say we have this divine view of the world. So we know all the information out there, like we know everything. And we also know that there are actually 200,000 yellow candies in this factory of candies, okay, out of a total of 1 million. So we know that that's 20% of the yellow candies, right? That's what we're doing, convert that into a proportion. Cool. These are the other proportions of other colors we have in our factory, but we're only focusing on the yellow candies. Now, 20% is the main number in the population. So some people will call that the population statistic. Some people will call that the parameter. In the book, they call it the parameter. But the thing is, right, the parameter, it's the thing that we're trying to find. It's the information that we're trying to find by extracting a sample from that population, right? So let's extract that sample. And it's a sample with 10 candies, as you can see here. And out of those 10 candies, 2 of those candies, that is 20% of those candies, are yellow. It's great. It's a sample that's very accurately representative of the population, which is something that happens not that often, but it does happen. And this is the main number in the sample, right? This is also known in the book as the sample statistic. So if we get the number 2 and we plug that into an ideal sampling distribution, which is a sample of main numbers that we got from many samples, right? We do that with sample number 1, we plug it there. We do that with sample number 2. Now we found 3 candies, so we're going to plug that in there. Plug 1, this third sample, we found 1 yellow candy. We plug that in there. And suddenly, if we do that 17 times, which is the example here, we're going to have a normal distribution shape, right? A bell shape. So we took our 17 samples, and now they're shaping this ideal sampling distribution, which is giving us the probabilities of finding a new sample, right? The question is, how different could my sample have been? That's the question that we're asking ourselves. Like, man, if I were to draw a new sample, what number would I find, right? If you get a sample now, it's interesting to know how rare it is to find that specific sample. So remember when we're doing that with height. So when we're talking about the height distribution, you can find your height and compare your height to the rest of the heights in the world. And you can say, oh, it's very rare to find a person as tall as me or as short as me, or like I'm actually average height. And it's very easy to find someone of my height. So that was the example that we're doing with height. Now we're doing that example with the main number that you find in your sample. So that's why people will get a little confused, but I hope you understand at this point that now we're trying to ask ourselves, okay, we drew a new sample and we found a new number, but how likely it is that we found this number? How rare is this number? So let's say your name is John and you're a middle school kid and you're really into candy, and you grab this bag of candies and you have 4 yellow candies. So you want to walk to your friends, you want to show off, okay? So you're going to go to your friends and say, hey man, this 4 yellow candy bag is very rare, bro. You should sell it on eBay because you're a middle school kid with a crypto side hustle or whatever. And the thing is, they're going to say, yeah, man, last time I bought 17 candy packs and only 2 of those packs had 4 yellow candies, which is the thing that you can see here. Out of 17 packs, only 2 had 4 yellow candies. So it's pretty rare to find that bag with 4 yellow candies. So you can impress your friends during your school break. And you can also sell this on StockX. It's that website where you can sell the valuable sneakers and stuff. So you could totally sell that there because it's rare. And with the sampling distribution, we're finding out that it's rare. Okay. So we know that the area of the distribution represents the chances that you're going to find a sample of certain value, right? So we know that these 2 4s here, these are the chances, right? 2 out of 17, the chances that you find a candy bag with 4 yellow candies, right? A 2 out of 17 chance of getting 4 yellow candies. 2 divided by 17, that's 0.11, also known as 11%. So we can translate them into percentages and decimals. We talk about this, right? So that's why we call this a probability distribution, because it's a distribution that's giving us a probability of finding a certain sample. And our expected value, so this is another term that they learn, this is another term that they teach you in the book, our expected value is always the tallest point of this distribution. So it's the midpoint of this distribution. What do we mean by expected value? Well, it's the value that you expect, right? If you were to buy a new candy bag, you would expect the highest chances that you're going to find 2 yellow candies, right? If you were to choose a single number. So if you're a gambler and you're in middle school and you're buying candy with your friends, you should bet on 2 if you're looking at this sample distribution, statistically speaking. And also if you are looking, at some time in jail. So this expected value is also called a point estimate, right? So the point estimate is this center of this distribution because it's the point that we're estimating that the population value is. Again, we don't know if that's the population value, but that's the most likely value. And again, remember that here we're talking about the ideal sampling distribution, not the derived sampling distribution. So we're going to get to that in a second. So another thing they talk about in the book is that the probabilities of all samples that you find, they always sum up to 1. So because 1 means 100%, yes, of course, we know that. Great. Now let's talk about continuous distributions. It's the same principles we had in this histogram thing, but now we can fit this curve on top of it. So it's just an area instead of a histogram, right? Because we can also find, let's say, the example that they give us is the weight of candies in the package. So the weight of candies could be any value between any sort of integers, right? So it's a continuum.